Hi everyone, we're going to start Module 8 today, which is all about exponential functions. And today's section 8.1 is going to be kind of our introduction. So let me start you off with a question that I think is going to help you see how an exponential function works. Imagine that you're offered two jobs for a month. We'll call it 30 days. Now the first job says, I'm going to pay you $10,000 a day, which is pretty good. The other job says, I'm going to give you a penny the first day you work, but then I'm going to double the amount of money you have for the next 30 days. You have to decide which job to take. So let's think about it. Now, the first job, you go, okay, I'm going to make $10,000 a day, 30 days, piece of cake. 10,000 times 30 would be $300,000. That's a lot for a month. So a lot of people would go, yeah, I'm going to take that, because they start thinking about it and they go, okay, let's see this penny job. Day one, I have a penny, and then I doubled it. So day two, I have 2 cents, 4 cents, 8 cents, 16 cents, 32 cents, 64 cents. By the end of a week, 7 days later, you haven't even made $1 yet. You have 64 cents. So you're thinking to yourself, forget that. I'm not going to take that. I'm going to take the $300,000. I'm going to take $10,000 a day. But that would actually be the bad choice. If you took that penny and doubled it for 30 days, you end up with over $5 million. And the reason is it's an exponential function. So if you think about it, this concept of multiplying times 2, 29 times, another way to write this would be to take my penny, which is $0.01, multiply it times 2 to the 29th power. That's what multiplying by 2 29 times means. That's what exponents mean. Now that thing right there, that 2 to the 29th power, that's what we call an exponential function. And that's the reason it got so big. After a week, we hadn't even earned $1, but after a month, you've earned over $5 million. And that's how exponentials work. So that first job where you are earning $10,000 a day, that's a linear function and has constant growth. Doesn't matter if you work 1 day, 7 days, 30 days, a million days, you're earning $10,000 a day, period. Job number 2 is an exponential function. It does not have constant growth. What happens is at the beginning, it grows very, very slowly. Remember, after a week, we had only earned 64 cents. But if you keep doubling and doubling and doubling, as it gets bigger, the amount that you gain when you double it gets bigger. So it's not constant growth. It's growth that starts out slow but gets faster and faster. And at a certain point, it'll be very fast. So here is an example of what an exponential function looks like, the green line right there. Imagine as time passes, that's how much money you have. So like right here, this is where I start. I have a penny. Maybe right here is after a week and I only have 64 cents. It's still almost nothing. And then over here is, 2 weeks and then 3 weeks. And then all of a sudden 4 weeks or a month, it's way up here. So that's where it started growing really, really fast. Now the linear one would have probably looked something like this. So again, after that first week right here, that's where it would have been better to have the first job. If you're only working for a week, that penny job is only going to give you 64 cents, and the $10,000 a day job is going to give you 70,000. So that's why the blue line is higher than the green line there. But eventually, you reach this point right here, where they meet, and at that point, the blue line keeps growing, but slowly. The green line is growing much faster. So as long as you're after that point where they meet, the exponential is going to make a lot more money. And that's how exponentials work. It's growth that's not constant. Okay, so here's what it looks like. If you're talking about an exponential function, we're going to say it's y equals b to the x power. And what makes it an exponential function is that the exponent is the variable. So you're not going to have a number there. You're going to have an x there, or maybe a t for time, or something like that. You're going to have the variable being the exponent. Now that number b stands for base, and that's what an exponential is. It's some number to the x power. It could be 2 to the x, 10 to the x, 100 to the x. That base can be any positive number except 1. It could be 1, but it's just not interesting because 1 to any power equals 1, so it's not really an exponential function anymore. So we're not going to do 1, and we're not going to do negatives. That would make it a very complicated function. That would be down the line for you guys. But any positive number except 1 could be b. Now I'm going to break it into 2 groups. I'm going to say if b is bigger than 1, then our graph has what we call exponential growth, and that's like the one we just looked at. That would be like this. This is a graph, I know it's typed very, very small there, but this says f of x equals 2 to the x. So this is a graph where the base is 2, and it's exponential growth, meaning imagine a point moving along this graph. You start right here, and as it's moving, it's growing, meaning getting bigger. Very slow at first, then a little faster, then a little faster, then a little faster, and faster and faster, and all of a sudden up here it's growing really, really fast. That's what we mean by exponential growth, getting bigger and bigger and bigger and faster and faster and faster. Now, if b is between 0 and 1, so b is less than 1, but can't be negative, so I'm going to say between 0 and 1, then what you have is something called exponential decay. And decay is the opposite of growth. Instead of getting bigger, it's getting smaller. So do the same thing. Imagine if I'm starting here and I'm moving along the graph, it's getting smaller. Down, 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 smaller, 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 smaller. And it flattens out here. And it's basically the exact opposite of exponential growth. It starts out shrinking very, very fast. And then it slows down and slows down and slows down and slows down, and it's still shrinking at the end, but very, very, very slowly. So instead of, whereas with exponential growth, it starts out flat on the right, and then it grows to the left. This is the exact opposite. It starts out very high on the left, and it flattens out on the right. Okay, let's talk about asymptotes. Every exponential graph has something called a horizontal asymptote. And an asymptote is an imaginary line that a graph gets closer and closer and closer to without ever quite getting there. So for our exponential functions, growth or decay, it's that horizontal line where the graph flattens out on one side or the other. Remember, it flattens out to the left for a growth function and to the right for a decay. But whichever side it's flattening out, that horizontal line where it is flattening out, we call that the asymptote. Just remember, a graph gets very, very, very close to an asymptote, but it never actually touches it. So when you're drawing the graph, just remember that you draw the graph kind of like blending into that asymptote, but it doesn't actually realistically ever quite get there. So we're going to learn through the rest of the module some tricks on graphing exponentials, but right now we're going to keep it real simple. I'm going to say for today, you're going to do some graphs in the homework. What I want you guys to do is, first of all, look at the base and decide whether it's exponential growth or decay. That's the first thing you have to do. If the base is bigger than 1, it's growth. If it's between 0 and 1, it's decay. After that, I just want you to make an XY table. Pick a couple numbers, try some different ones out. I mean, that's how it works with an XY table. Pick values for X, find some Ys. If you get a number that's really, really big and it doesn't fit on your graph, pick a different X. But try to find a few X's so you can see that curve shape and you can draw it in. And then one important note, this is a tricky thing about exponents. Any number to the 0 power doesn't equal 0. It equals 1. So for example, if I had 5 to the 0 power and I asked you what that is, a lot of people would just say 0. They go, okay, it's 0. Or they might say it's 5. It's actually neither of those things. 5 to the 0 power equals 1. And that's for any number. If I had 1,000,000 to the 0 power equals 1. So that's a math rule that you want to remember. It's a very important one. You want to remember it because you're going to be using it for as long as you do math. Any number to the 0 power equals 1. All right, so let's do our graph. we're going to graph y equals 3 to the x minus 4. We're going to do it using an xy table. But the first thing I do is I look at the base, which is 3. I say 3 is bigger than 1, so this is an exponential growth function. So this one's going to be flat on the left side and turning up on the right side. Now once I know that, let's try to find the shape of it. Let's make a quick xy table. And remember, for an xy table, you can pick any numbers you want. I'm going to start with 0 for x. I like to start with 0. So every time I pick a number, what I'm doing is I'm plugging it in for x right here. So I'm going to have y equals 3 to the 0 power minus 4. And this is why I just went over that rule with you. 3 to the 0 power equals 1. So I get 1 minus 4, which would be negative 3. So when I plug in 0 for x, I get negative 3 for y. That's my first point, 0 comma negative 3. Let me draw a blank graph over here. Okay, so my first point was 0, negative 3. That would just be down 3, right there. Now I need another point. So maybe I'll pick 1 for x. That's another good x value. And again, I'm going to go back up here and I'm going to plug in 1 for x. So I get y equals 3 to the first power minus 4. Now 3 to the first power is just 3. Anything to the first power is itself. And 3 minus 4 is negative 1. So there's my second point, 1 comma negative 1. That would be over 1 down 1, be right here. Now, I'm going to do one more point. Let's say I pick 2 for x. So I get y equals 3 to the 2, or 3 squared, minus 4. 3 squared, 3 times 3 is 9, and 9 minus 4 is 5. So my next point is 2 comma 5. That would be over 2 up 5 up here. And you can see how I found that exponential curve shape. Now, if you start plugging in negative numbers for exponents, it gets tricky. If you have to do it, use a calculator. We haven't really learned negative exponents yet. Like if I wanted to plug in negative 1 for x and see what I get, use a calculator for now. But remember, because we know it's exponential growth, we don't really need to, because I know this thing is going to flatten out on this side like this. So that's what I would do. It's just flatten it out. Once you know it's exponential growth and you found the curve that's going up to the right, flatten it out to the left. Now in the homework, you're going to be asked to label 2 more things. One of them is the y-intercept. And the y-intercept is what you get by just plugging in 0 for x. So for this question, the y-intercept is 0 comma negative 3. And you're also going to be asked to tell where the asymptote is. For now, just give it your best guess. The asymptote is this horizontal line where it's flattening out to the left. And I would say that's at about negative 4. So for this question, I would say my y-intercept is 0, negative 3. That's for sure. That was one of the points on the graph. And the asymptote is negative 4. And that's what we're going to do. We're going to use what we know about exponentials, what we learned today, to try and draw a sketch. It may not be perfect yet. We'll learn some better tricks on graphing later in the module. But for now, we want to focus on number 1, whether it's growth or decay. Number 2, using a XY table to find the shape of it. And then number 3, tell me what the y-intercept is, and tell me what you think the asymptote is, your best guess for that.